Hello everyone, and thanks for your interest in my talk titled Frequency Effects in Diachronic Vowel Shifts Are Tiny. And really, that title sort of summarizes the main message of the talk really well. But I also included a quote here, and that's just to give you a sense for the underlying motivation for this talk. And I'm not going to read it out, but we're going to talk about sort of p-values versus effect sizes a little bit more in depth later on. So because this talk is about frequency effects in a certain type of sound change, it's important to be clear about what we mean when we talk about frequency effects in diachronic vowel shifts or in phonetically gradient sound changes, which is really what we're talking about here. So here's an example, a really simple one. Let's say we have a vowel that, at a given point in time starts out as a back oo, right? And then over time, that back oo undergoes fronting to become something more like an oo or an oo. Now, because we're talking about frequency effects, what we're assuming here is that there are some low frequency words with that vowel, and there are also some higher frequency words with that vowel. And in this specific scenario, the low frequency words by the end of that time period sort of don't progress quite as far as the high frequency words do. Okay, so this would be a case of a frequency effect in a phonetically gradient sound change. Okay. We also have a little sort of cartoon illustration of this over here on the right side, where we've got year of birth plotted on the x-axis and then F2 correlated with frontness on the y-axis. And what you can see here is basically the same stuff that you did in the vowel chart, which is that low frequency words are essentially changing slower than high frequency words. And recently, there has been a recognition of the fact that when we are talking about frequency effects in sound change, it's this kind of relationship that we're interested in, where maybe we start with some kind of a frequency effect at the start of a period, but crucially, that frequency effect changes over time. So in this case, the high frequency words are actually increasing their advantage. And that's because if you only observe a static effect, then that really doesn't tell you anything about change, right? Like that static effect could be just due to some kind of an online factor in speech production that has nothing to do with sound change at all. Whereas if you observe something more along these lines, then that would be telling you that that change is really affecting the lexical representations of those words. And then that has further implications suggesting that maybe phonetic detail is stored not just at a sort of a phonological category level, but even in the representations of specific words. So in summary, when we are looking at frequency effects in phonetically gradient sound change, it's not enough to just look at snapshots, right? We can't really just look at, say, what happened in the early 1900s and then stop there, right? Or we can't really just look at what happened at the end of this time period and just stop there. We actually need to see how that frequency effect itself changes over time. So the strategy that we're going to take here when we're talking about frequency effect is that actually we're going to talk sort of about both of these things. So we'll look at that interaction that I just mentioned, and also we'll be talking about the average effect of frequency over a given period, because although that may not necessarily tell you about whether a change is affecting word-specific lexical representations, it is still basically a prerequisite to observing any kind of frequency effect, right? Like, so for instance, if you look here in this graph, there is an average effect over the period insofar as high frequency words throughout the entire period do have an advantage. Okay. So when we're talking about effect sizes, we'll be talking about these two different things. So why focus on frequency effects in sound change? Well, I mean, for starters, they are among the best known examples of word-specific phenomena. Also, if you look at usage-based models and exemplar models and various other models that have to do with word-specific representations, they often make very specific predictions about what you might expect from, say, high-frequency words versus low-frequency words in different types of sound change. And then what we actually find in those sound changes has important implications for these models. And then finally, there is a lot of debate about frequency effects in phonetically gradual sound change. And indeed, a lot of researchers, some of whom are listed on the top line here, have looked at different instances of phonetically gradual sound change and didn't really find any evidence for strong frequency effects. Whereas other people listed on the bottom line here have looked at other cases of phonetically gradual sound change and did find some evidence for frequency effects. And I think there's an important point to make here, which is that there are these sort of two sides to this debate, but I think a lot of the time the two different sides don't really engage or only engage superficially with the evidence from the other side. And I think that's problematic. We really have to look at the totality of the evidence that we have right now. And that is actually really interesting, but also very confusing. We have these examples where it's not clear whether there is a frequency effect, or it's clear that there isn't one. And then we have other examples where there does seem to be something. Yeah. And then there is another important observation, and this kind of leads us back to the topic of this presentation, which is that when we do find frequency effects, a lot of the time they do seem to be relatively small. And that's really one of the main motivations for this talk. What are the potential issues with frequency effects, and these very small frequency effects in particular? Well, the first of them is the file drawer effect, which is a really simple phenomenon that's just due to the fact that it's very hard to publish null results or non-significant results. And anecdotally, this has certainly happened to me. I have carried out research on sound changes looking for frequency effects where I didn't find such an effect, and that work is not published anywhere. And I've certainly talked to others as well who have run into the same kind of problem. And really, the kind of situation that this creates is that when you look at the literature, a lot of people are reporting frequency effects, and it kind of seems like, a good portion of the people who are looking for frequency effects, in fact, do find them. Right? We've heard about other results where they weren't found, but in a lot of the work on frequency effects, it's positive results that we are hearing about. But in fact, there's all of those negative findings that just don't make it into the literature, and that just means that we don't know what the proportion of the true positives is. The second issue is the equation of theoretical significance and statistical significance. And what this means is that maybe it's best understood through an example that I have here. If you look at the top graph here, this is kind of what one expects to see when they hear that, someone found a significant frequency effect in a phonetically gradual sound change. So what you see here is those thicker lines, they represent some kind of model predictions or an average pattern. And then the thinner lines, they represent what individual words are doing in this sound change. So each of those thinner lines is a frequent word here, I think those are the blue ones here, or a low frequency word, which are the red lines down here, right? And in this case, the sort of average pattern is really nicely aligned with what the individual words are doing. But what we often actually find in reality when we look for frequency effects is a lot more like this, right? When we have an average pattern that is maybe significant, but the individual words are doing all kinds of different things. And, in general, when you just look at the individual words, you don't see much of a pattern at all. And I think that the main problem here is that when you have a case like this, I don't think we are justified in developing a sort of an elaborate theory of frequency effects that is really focusing on those tiny effects that we are finding there, right? Or if we do develop such a theory, that theory also has to explain why those frequency effects are so small. So what else is happening that means that, by and large, what we're observing is actually more like a neo-grammarian change, and then we have this slight undercurrent of a frequency effect that goes with it. And then finally, we have the issue of ambient correlation noise. And I have another quote here from Cohen, which is that the null hypothesis, taken literally, is always false in the real world. If it is false, even to a tiny degree, it must be the case that a large enough sample will produce a significant result and lead to its rejection. So when someone hears this, and that was certainly my reaction when I heard it for the first time, I think it kind of sounds wrong, right? Like our statistical tests significance shouldn't be a function of the sample size. If there isn't an effect, it shouldn't matter whether we're looking at a large sample or a small sample. We just shouldn't find that effect. And what Cohen is saying, that in theory that's true, but when you look at the real world, and especially at human behavioral data, things just don't work out that way. And that's because every variable is correlated with every other variable, right? Those correlations are there, and that's certainly true for word frequency. If you look at word frequency, it's correlated with informativity, with word durations, with various prosodic factors, and all of those factors potentially could have a confounding effect. It could be the case that what we are identifying as a word frequency effect is actually a result of prosody or some of these other effects. And crucially, the smaller the effect that we're looking at, the more severe this danger is. That in fact what we're observing is just the result of a confound. So let's now turn to our current project. I looked at 3 different data sets: the origins of New Zealand English corpus, the sounds of the city corpus, which are samples of Glasgow English, and a corpus of Derby English. I automatically extracted and filtered single point F2 measurements for a number of different vowels from each of these corpora, and then ended up keeping only a subset of those vowels because not all of the vowels actually showed changes in the time period that I was looking at. So in the dataset that I ended up with, we have goose, kit, dress and trap from New Zealand English, goose, fleece, face and strut from Glasgow English, and then goose from Derby English. So now that we have our 9 vowel categories that we are looking at from 3 different varieties, what I then did with these vowels is I sort of restricted the time period that I looked at. Each of these corpora are diachronic corpora, so they have recordings from speakers born at different times. But I restricted the time period separately for each of these vowels, looking only at that portion where the vowel was actually showing change, right? So if it was stable afterwards, then that would not be included in this analysis. And I ran 2 different regression analyses for each of these vowels. The first one is looking at by-word average F2 values. And I did this mainly so that I could extract an R-squared value for frequency, as well as previous context and following context in these sound changes. And what we're going to do is that we're going to compare this R-squared value for log frequency with previous context and following context, and just to get a sense of actually how much work frequency effects are doing. And then in the second set of models, these are regression models on by token F2 values. So there's no averaging here. We're just looking at the F2 measurements for each of the tokens. And these models include an interaction between time, which is usually year of birth, and log frequency. And what this allows us to do is to actually look at those potential changes, potential differences in the speed at which low frequency versus high frequency words are changing. So actually what I'm going to do is I'm going to be comparing the size of the overall change in a vowel category versus the change in the frequency effect itself, right? So what kind of frequency effect do we start with, and does that frequency effect change? In other words, do high or low frequency words increase or decrease their advantage over time? So here we go. These are the results from the first set of regression models. So this is the one where we are looking at R-squared values. And let me just very quickly say what I did here. So I took each of these vowels, and then I fit the statistical model to the by-word average F2 values. So each of the words would be 1 data point in this data set. The predictors in this model were preceding context, following context, and log frequency. Okay, and then I also fitted subset models where I would exclude each of these predictors, and then I would check how much excluding a given predictor changes the R-squared value of that model. In other words, essentially, how much of the variance is accounted for by a specific predictor. Okay. And then I have those values listed separately for the three predictors. So we've got the preceding context values up here, the following context values in the middle here, and then the log frequency values in the bottom here. The overall pattern is pretty clear here, and that's that preceding context and following context do account for more of the variance than does log frequency. And maybe that's not a surprising finding, but one thing that's important to bear in mind here is that the scale that we have on the x-axis here is a log scale, right? So actually when we say that there is a difference, this graph is maybe a little bit misleading in that it doesn't seem like a huge difference, but it's actually quite a big one. If you look at preceding context and following context, they range between 2.3% to 16% with a median of 6.8% for preceding context, and between 0.2% to 16.4% with a median of 2.4% for following context. Now, if you then compare these with log frequency, those range from 0.03%, which is essentially nothing, to roughly about 2% or 2.15% for Glasgow strut. So while there's a little bit of overlap between log frequency and following context, by and large, preceding context and following context are much more reliable predictors of these byword average F2 values in these different categories than is log frequency. Overall, it's safe to conclude that when you're looking at these static frequency effects, and so we're not looking here at the interaction between frequency and time, when you're just looking at these static frequency effects, they tend to be really, really small. So far we've looked at these static frequency effects, but we also said before that that's not really what we're interested in when we are looking at frequency effects in sound change. So we do expect to see static effects, and perhaps we do expect them to be slightly larger than what we observed here. But the focus is usually on how frequency effects change over time, and whether we see high or low frequency words increase or decrease their advantage over time. So that's what we're looking at in this graph. And let me just try and break this graph down for you. So what we see here is each of the rows corresponds to a different instance of sound change. So we've got Glasgow fleece and Glasgow face, etc., etc. And then for each of those instances of sound change, I am plotting two different pieces of information. So those grey arrows that you can see there, what they are showing you is what's happening to that category overall, independent of frequency. Okay. So in this case, for instance, this grey arrow is telling you that fleece has been moving in a positive direction with respect to F2, so probably undergoing some kind of fronting. Whereas strut has been moving in a negative direction, maybe undergoing backing or rounding. Now, the way that this information is presented is actually in a standardized format. And that standardization means two things. One of them is that I took the F2 values and I just centered and scaled them, right? So subtracted the mean and then divided by the standard deviation. And then once I had those standardized F2 values, what I then did is that I basically looked at the key predictor here, which, when you're looking at these gray lines, is time, which is usually encoded by year of birth in this data. And I took a point that's sort of at the lower end of the spectrum for that predictor, and then another point that's at the higher end for that predictor, right? Which was actually defined as the mean minus one standard deviation and the mean plus one standard deviation for year of birth. And then I looked at predictions for the standardized F2 at those two different time points. So what you can see here is that between the sort of older speakers and the younger speakers for face, we see about one standard deviation increase in F2. That's what this is telling you. But of course, the interesting part of this graph is not the overall changes, but how those overall changes compare to the frequency effects. And for the frequency effects, you can actually see two different bits of information. You can see these arrows which have a blunt and a pointy end. And those blunt and pointy ends, what they are telling you is how the frequency effect changed over time. So the blunt end is telling you what the frequency effect looks like at the sort of closer to the beginning of the time period. And here you can see that in this case, that frequency effect is aligned with the direction of the overall change. So we have high frequency words in the lead. But then over time, as you move towards the end of the sound change, the pointy end is showing you that by the end of that time period, that relationship turns around and now you have low frequency words in the lead. There's also a bit of color coding here. This arrow is in black, and that's telling you that this effect was not significant in the model. That is to say, the interaction between time and frequency did not come out as significant. Here's another effect that is significant. This is the one for strut. So here we start again aligned with the direction of the sound change. So here we've got a sound change that's in the direction of in the negative direction with respect to F2, and the frequency effect is in the same direction. So initially high frequency words are in the lead, but by the end of the time period that relationship reverses, and now we have low frequency words in the lead. This is kind of an odd finding. I'm not sure if there's any specific model that would actually predict this. The other significant finding that we have is for Derby Goose. And here what we see is that, again, we start out with a frequency effect that's aligned with the direction of the sound change. So we've got high frequency words in the lead, but by the end of that time period, that frequency effect basically just disappears. So what can we see overall in this graph? Well, what is pretty clear is that frequency effects in general are very small compared to the overall changes. And in the small number of cases where they do seem to be a little bit larger, not by any means huge, but a little bit larger, actually what we find doesn't really align with any predictions from existing models of frequency effects. Maybe what we observe for Derby Goose here can be explained as a sort of a ceiling effect, but even that's not 100% clear. And certainly what we see for strut, where we start with a relatively strong effect where high frequency words are in the lead and then that turns around completely, that's not something that I think is predicted by too many models. So in conclusion, it seems that frequency effects in diachronic vowel shift are indeed tiny. Whether you're looking at the sort of static realization of that effect, or if you're looking at how that effect changes over time, we don't see any huge, really substantial frequency effects. Now, it does need to be stated that these findings are preliminary. We need to look at more instances of change, and also it would be great to actually compare what we see in the actual sound changes with predictions from models like the ones presented in an excellent paper by Todd et al., or models from other papers. But even though the findings are preliminary, I do think that there are some potential implications. To start with, I think we should be asking ourselves the question of whether frequency effects should remain these sort of poster children of word-specific factors in sound change. Maybe some people don't consider themselves to be the poster children, and that's fine, but I think a lot of people do. When you talk about word-specific models and factors, we kind of often automatically go to frequency effects. That could be a problem, or at least looking for frequency effects specifically in phonetically gradual sound change. Well, maybe that's not the best example of word-specific factors in sound change. A second point is that maybe there is some kind of a non-linearity in frequency effects that we're not capturing. And what I mean here specifically is that it could be the case that it's extremely high frequency words that are doing all the exciting stuff. And when you look at these sort of foot soldiers of the lexicon, right, so those kind of mid-frequency ranges and not really focusing on those high-frequency words, and maybe even explicitly excluding them from your data as function words or for some other reasons, then maybe you're just not capturing sort of the essence of frequency effects. And I think in this workshop, we are actually going to see some examples of people looking at very high-frequency words, and I'm really looking forward to seeing how those turn out in terms of their behavior. And then finally, and I think this is very clear from this work and also just more generally, I hope that this is something that we can all agree on, we need to be methodologically rigorous in our analysis of frequency effects in sound change. So we need to try and avoid the file drawer effect. Next time you find a null result, please try and report it. We need to avoid sort of increasing our researcher degrees of freedom. So we shouldn't sort of try and treat data exploration as if it was confirmatory hypothesis testing. And we should be starting with solid predictions and kind of building our work on top of those solid predictions. We shouldn't just say, well, let's look for some kind of a frequency effect. We should actually try and derive what kind of effect we're looking for from a specific model. So I'm going to leave you with those conclusions. Thank you very much for listening.